In this video we will discuss about the Turing machines. So if we can take a look here, now till now we have seen that these kind of languages, or we can say the regular languages, these languages are recognized by or accepted by final state machines, either it is DFA or it is NDFA. Now when we talk about the context free languages are just recognized by PDA, or we can say the non-deterministic push down automata. Now if we see that a to the power n, b to the power n, for that language we can just create a PDA, or if we are having a language which is described by this expression WWR, we can also create the PDA for that. Now if we are talking about such kind of languages, a to the power n, b to the power n and c to the power n, so you can see that by pumping lemma we prove that a to the power n, b to the power n, c to the power n is not belongs to context free languages. So it does not belong to the CFG class. Now if we talk about this WW, so we are having two strings, or we can say the concatenation of two strings. Again, we cannot create a PDA for such kind of languages. Now when we talk about the PDA, there is a memory issue in PDA, that we are having only one stack. Okay. Now in FSM we are not having any kind of memory, so we cannot store a particular input into the FSM. That is why we cannot create a PDA or a finite automata for such kind of languages. Now when we talk about such kind of languages, these languages are belongs to the CSL class, or they are unrestricted languages. Now when we talk about such kind of languages, we can have, or we can generate a Turing machine which can accept these languages. So today in this video we will discuss about the Turing machine, that what is the transitions we can use into Turing machine, or how we can create a Turing machine. So when we talk about a Turing machine again, it is a kind of machine. Now the difference between a Turing machine and a push down automata is, when we talk about the push down automata, we generally use a stack in which we keep a record of certain symbols of the string. Now in this Turing machine we generally have a tape. Now this tape is arranged in a linear manner, where each memory block is represented by a cell. Now when we talk about the control unit of this control unit contains certain states, and every time if we are reading certain input, and we are reading certain input every time, we write certain output or certain symbol onto this tape. So there are two operations basically that happens on this Turing machine or on this tape. The first operation is reading certain symbol from the tape, and then second operation is writing certain symbol on the tape. Now at that particular moment we change a state. So let's suppose this is your Q1 and this is your Q2. So we generally change a state. Either we just remain at the same state, and or we can change a state. That depends on the operation we are performing or the transition we are performing. So when we talk about this read write head, read write head can move left or right. Now if we are talking about the earlier machines, in those machines the read write, there was no such thing like read write head. So the head was only moving in one direction, that is from left to right. But in Turing machine, this read write head can move to left side as well as to right side. So suppose if we are at this cell, let's say this is C1, so we can move from C1 to C2, that is on the right side, or we can move from C1 to C3, that is on the left side of the current cell. So there are three operations basically we do. We read a symbol, and then we write a symbol, and we move to left or right side of the existing cell. So just take a look at this example. Now in this example what is happening, initially the read write head is at this cell which is having this A. Now what the machine is doing, it is reading A, and at the same time when it is reading A, it is writing K. So in place of A, it is writing K. Now after that the control is moving towards the left side. So the three operations we are doing, we are reading A, we are writing K, and then the read write head is moving towards the left side. So now this read write head is pointing at cell which is containing B. Now, in this example, at B, what we are doing? We are reading this B, and after that, after the reading of B, we are writing the F symbol in the same memory cell, and then we are moving towards the right side. Now, whenever we are talking about the Turing machine, at the initial state, at the start, the head points to the leftmost position of the string, or the cell at which the leftmost symbol is stored. So, suppose we are having this input string and this A is available at the leftmost position, then initially the head will point to this A. Now, there is also one thing, that the input string is never empty. So, we must have certain input in the tape to process or to create a certain Turing machine. Now, the transitions, they are allowed basically. So, the transition is shown graphically as like this, where we are having a Q1, the state, and a Q2, another state. We are changing from state Q1 to Q2, and over this edge we are having 3 symbols. The one symbol is what? Read. So, this is the symbol we are reading, and the second symbol, this B, this is the symbol we are writing on the tape, and this L represents the direction of the movement of the tape, of the head of the tape. So, if this is L, then the head of the tape will move towards the left side, and if this is R, then the head will move towards the right side. So, in this example, if we are representing this as this graphical representation of this transition, what we are having? We are in the current state is Q1. So, currently we are in state Q1, and the head is pointing to A. So, the meaning of this is we are at Q1 state and we are about to read the symbol A. So, if we are reading this symbol A, after that what we are going to do? We will write the symbol B and we will move towards the right side. So, if we are reading this symbol A, then at this position, which is this position, we are writing the symbol B, and now we are moving towards the right side. Now, for this transition we are having another transition, and for this transition what we are doing? We are the current state is Q1, and the input head is the read write head is pointing at symbol A, and we are reading the symbol A, then we are writing B in place of A, and then we are moving towards the left side. So, this is how the transitions of Turing machine can be done. Now, you can see there is a specific symbol here which is represented by this representation, and here we are using this representation, and in some books you will find out that the square is also represented for this representation, and now what this represents, it is just a empty space. So, let us suppose the length of the tape, it is assumed to be infinite. So, at some position we are having our input or the string we are going to process, and after that, before that string and after that string, we are having certain empty spaces, and those empty spaces are represented by certain specific symbols, and you will find out that each author is using the different kind of symbol to represent those empty spaces. So, in this transition what we are doing, we are in the current state is Q1, and the head is pointing to the cell which is having an empty space, and while reading an empty space, after reading an empty space, what we are doing? We are writing the G in place of that. So, in place of this symbol, what we are writing? We are writing G, and the next movement is towards the right side, and after that we are changing the state, and now the state is Q2. So, the Turing machines are deterministic in nature. So, there is no non-determinism is allowed in Turing machine until unless we are using certain variant of a Turing machine. So, if we talk about this determinism, the allowed transitions are in this form. So, for a input symbol we are having only one transition. So, suppose if we are having an input symbol A, then for input symbol A we will have only one transition, and for another input symbol we will have another transition. It is not allowed that for a certain input symbol or common input symbol we are having 2 transitions. So, this is not allowed. So, we can have these kind of transitions, but we cannot have these kind of transitions. Again, no lambda transition is allowed. So, as a empty string is not allowed, that is why the lambda transitions are also not allowed in Turing machine. So, this is an example of partial transition function. Now, it may be a situation that we are Suppose in this case what we can see, the input symbol are A, B and C. And just take a look here, at this state Q1 we are having the transitions for input A and input B, but we are not having transition for input C. So it is okay to not have a transition for a certain input symbol. Now if you recall the DFA, so in case of DFA what we have, in case of DFA, for each and every input symbol we must have a transition at a certain state. But unlike this DFA, in Turing machine, if we are not having any transition for any input symbol, then it is okay. Now the halting, at a certain state machine halts. Like suppose after reading input in this transition, we can see that after reading input A, we are changing from state Q1 to Q2, and after reading input B, we are changing the state from Q1 to Q3. Now let's suppose the input head is at input C and we are in state Q1. What will happen? Now we are not having any transition for the state Q1 when we are reading input C. So in that case the machine will halt. So that is known as the halting of the machine. So if the machine halts, if there are no possible transitions to follow, if you are not having any further transitions for a certain input from a certain state, then the machine stops at that particular state and the further operations will not be performed. So we just call that state as a halt state. Now you can see here with the example we have discussed earlier. So now if we are at the current state Q1 and the read write head is at symbol C, in that case there will be no possible transition and machine will halt. Now when we talk about the final state, again there are certain restrictions about the final state in this Turing machine. Now if we are having certain transition from other state to final state, that is allowed, but we cannot have a transition from the final state. So there must not be any outgoing transition from the final state, that is not allowed in the Turing machine. So why it is that? Because whenever we reach at the final state, the machine will halt. So when we talk about the acceptance of a certain string on this Turing machine, then the Turing machine will accept an input if machine halts in a final state. Now if machine halts in non-final state, and there may be a certain situation that if the machine enters an infinite loop, in both the cases we will reject the input. So just take a look at this example where we are just checking for a acceptance of a language. So if our language is in this form, in this expression, what we are going to do? So this Turing machine is going to accept such kind of languages. Now this Turing machine is having two states, Q0 and Q1, and at Q0 we are having two transitions. So if we read input symbol A, in that case we will write the input symbol A and we will move towards the right side. So we will trace the input, and if we are finding out the empty space, then we will write the empty space and we will move towards the left side, and at the same point we will change the state from Q0 to Q1, and this will happen when we will trace out the complete input. And this, when we reach this at this Q1, we will say that the machine is accepting the language, the particular string or the particular input. Now just take this example. Here we are having an input string that is having three symbols, that is A, and initially we are at state Q0. So after reading A first time, we will write A at the place of A, and the read write head will move towards the right side. Now at the second transition, what will happen? Again it will read A and write A and move towards the right side. And now at this position, again it will read A and write A and move towards the right side. Now at this position it will read an empty space, and when it is reading an empty space, this transition will follow, and after reading an empty space, it will write an empty space and move towards the left side. And when it will move towards the left side, the machine will change the state and it will reach to state Q1, and at this Q1, it is a final state, the machine will halt, and we can see that when the machine is halting, it is halting in the final state. So we can say that this input is accepted on this machine. Now we are now just take a look at this regex example. Now what string we are having? We are having ABA. Now when it is reading input A, it will write A and move towards the right side. Now at this particular point, the input to be read is B. So we are going to read the input B, but there is no transition possible for input B in this Turing machine. So at this particular point, as we are not having any possible transition, the machine will halt, and the machine is halting at this state Q0. So that is why it will reject the input. So now we are going to discuss the formal definition of Turing machine. So when we talk about the formal definition of Turing machine, again the Turing machine is represented by 7 tuples, where we are having Q represents the set of states, then we are having this sigma, which is representing the input alphabet, the set of all the input symbols, then we are having this gamma, this is the tape alphabet, which is containing set of all the symbols which can be written on the tape, then this del, it is a transition function which is representing the transitions we are having. Then we are having this Q0, which is the initial state of the machine, and this symbol is the blank symbol or blank space, and then we are having this F, which is having the set of final state. Now at this point we are having this sigma and this gamma. So it is assumed that this sigma is a subset of this gamma. As we can have the same the symbols we are going to write on the tape, we can write the input symbols as well as we can write certain another symbols which are other than the input symbols. So there may be situations, and we will see certain examples about that. So for that situation, we can say that sigma is a subset of gamma, or we can say the input alphabet is a subset of tape alphabet. Now just take a look at the transition function. Now whenever we are representing the transition in this graphical way, we can write that transition in the form of del function. So what we are doing here, we are writing del q1. So currently we are at state q1, and what input we are reading? We are reading this A. So we will write A here. So it will be del of q1 A is equals to the next state, what state we are reaching at. So next state is here q2, and what symbol we are writing? So currently we are writing this symbol B, and then what is the direction of next movement? So the direction of next movement is R. So in general, the transition function can or a transition rule can be defined as a del, then state, then an input symbol read, which we are reading, which is equals to the next state, comma, the symbol we are writing, comma, the direction we are choosing to move further. So it will be A R or it will be L. So in this transition, we are at a state Q1, and then we are reading this symbol C, and we are reaching to state Q2, and we are writing the symbol D, and then we are moving towards the left side. So this is how we can represent a transition rule in a form of this del function. Now along with that, there is an important thing in case of Turing machine, that a certain point of time the state of the Turing machine can be described by the instantaneous description, or in short form we also call it as ID. So if a certain machine is in a certain state, at that point of time there must be certain input which the machine has read already, and there must be certain input or the certain string, or we can say more specifically a substring which is yet to be read. Then by combining all those three, we can just describe the instantaneous description of a certain machine. So just take a look at this example. What we are having? We are having CABA. That is the string which is available on the tape. Now the current state of the machine is Q1. We are in Q1 state, and the input, the read write head is pointing at B. So it means the next input which we are going to read is B. So before that, in the left side we are having CA, and in the right side, along with this symbol which is pointed by the read write head. So let's suppose this is your substring X, and let's suppose this is your substring Y. Okay. Now we can represent this as x q1 y. So this x is the substring which is available on the left of the read write head, and this y is the string which is available on the right hand side of the read write head along with the read write head. So we can also write this x q1 y as x q1 some symbol, let us say a and y. Now in this representation what we are doing, we are assuming that the substring which is after the input out read write head is represented by y, and we are representing this symbol by a, and before that we are having x. So this is representing that the x is available before the read write head, and we are available at this state q1, and the next input we are going to read is a, and after that the string which is yet to be processed is y. So for this example, the instantaneous description can be described as CA Q1BA. So this CA which is available on the left side of this read write head, and we are at this state Q1, and the input symbol we are going to read is B, and left string which is available at the right hand side is A. Now by using these IDs we can just describe a move. So if we are taking a look at these examples here, what we are having, we are in state Q2, and the input we are going to read is X. So the machine is described by this ID. The machine is in Q2 and the input is to be read is X, and after that we are having A, Y, B. Now after one move, you can see here that we are changing from state Q2 to Q0, and at the in place of this input symbol X we are writing X, and the input type the read write head is moving towards the right side. So the next symbol which we are going to read is A. So this move can be represented by this ID. After this ID, if we are moving or we are making a single move, we will reach to this particular state, that X, now X is on the left side of, and this Q0 is the current state, and the next input we are going to read is A, and the left out string is YB. So you can see all those moves which we are representing using the IDs. So initially we are at state Q2, we are going to read X, and the complete string which is after this X is AYB. So that is described by this ID. Now after single move we will reach at this configuration, and this configuration is defined by this ID, where we are having X on the left of the read write head, then we are in state Q0, and after that we are having string AYB. Now after that we will reach to this configuration. Now at this point what move we are doing, we are reading A and we are writing X in place of A, and we are moving towards the right side, and we are changing the state to Q1. So that will be represented by X X Q1 YB. So after one move, X X Q1 YB will generate X X Y Q1 B. Now what we are having, this symbol is representing a single move. Now we can generate we can represent multiple moves. Now if we can see from here that from this ID, what is generating? This ID is generating. So we can just represent that whole move, all the derivations by a single move, and that is represented by this symbol. So from this ID we can generate this ID. Now there may be in certain books, certain authors use this symbol to represent a single move and this symbol to represent multiple moves. So that's it in this video. In the next video we will discuss certain examples of Turing machine. So thank you.